So, we've learned about the time dilation, the time tick at a different rate for the different observers. Today we'll learn about the length contraction. That's another big thing happening with the relativity. But again, all experiments proving that it's true. So again, let's consider two people, one stationary on the Earth and another flying by in the spaceship. And person here has again light clock, which we were using when we were talking about time dilation, but this time clock will be positioned not vertically, will be positioned horizontal. So person here has this light clock and light going this way and back. And because person observing this clock is stationary relative to this clock, that will be a proper time measured by that person. Because if you're stationary relative to the clock that you're observing, it's a proper time. And let's say the length, the distance between the mirrors is L0. So we will have that time measured will be equal to 2 times L0. Time measured for light go from one mirror to another in return to the first will be double length of the clock divided by the speed of light c. Very simple. Time equal distance over speed. Yes?
Is this for the person on the Earth?
We're talking about the person who on the Earth has this clock and observing this clock. Now, on the spaceship again we have absolutely identical clock. But now person from the Earth and this spaceship moving this direction with the speed v. And now the person from the Earth looks on the clock on that spaceship. So we have this clock, but while light traveling from here, from A to B, spaceship moving this way. So when light will hit this mirror, it will be at this position, C. So that what observer from the Earth will see, that the light travels bigger distance, right? Because this mirror moves. Now, when light bounces back, and this moving, so then person from the Earth, stationary, will observe that light now travels back to this mirror, shorter distance. Because the clock moving to the right. So when it comes from here to the right, from the left mirror to the right mirror, it will travel longer than the distance, than the length of the clock. Because this mirror, by the time light comes to it, it's moved away. So distance is long. Then when it bounces back, this mirror moving this way, so this distance will be short. And let's say this is D. So what will be the distance from A to C? Distance from A to C equal length of the clock plus speed of the spaceship times time to get from A to C.
L is like L over. Is it the same?
It is the same length, yes. L0 plus, it's traveled some extra bit, this extra bit will be V times time from A to C. Now, on the way back, so distance CD will be equal now L0 minus V times time to travel from C to D.
Wouldn't?
Because it travels shorter distance. This clock moved to the right, so it travels shorter distance. Make sense? So from first point of view of per stationary person, this.
Oscar Goldman, please come to reception. Oscar Goldman.
So this distance is greater by that much. That's not the same time at different times. Because travel from A to C is not the same as travel from C to D. But this distance is shorter because when light was coming back, mirror moved there. Make sense?
Yeah.
Now, what will be the total time from the point of view of the person who is on Earth, or the total time to get from A and then to D? We just need to add, let's rearrange those formulas, TAC. TAC, total time will be TAC plus TCD. That will be the total time observed by the person on Earth. Light came from A to C, and then from C to D. Just add those times. Let's rearrange those formulas. And we have...
So is T equals TAC plus TCD, is that from the Earth's perspective?
That is person from Earth
So
looking on the clock on the ship.
Improper time.
No, it's not proper time when person on Earth looks on his or her own clock which is stationary. It's not a proper time. It's a time that measured to move.
Yeah.
So we have now, but what this equal? This will be equal C, this distance. We have distance equal speed times time. So speed of the light times TAC.
Is it AC plus CD?
Times the same time. AC equals C times TAC, CD equals CTCD. So then rearranging, we have CTAC equal L0 plus VTAC, and from this we have CTCD equal L0 plus VTCD. Then let's rearrange each formula for T, minus, yes, minus. Let's rearrange each formula for TAC and TAB. TAC, again, you don't need to derive the formula. You will need to use what we will get at the end. Just showing where it's coming from. TAC from the first equal, TAC will be L0 divided by C minus V, and we have TCD equal L over C plus V. And the total time, the L0 is the length of the clock that appeared to the observer from the Earth. It's not A. This is L that a clock appeared for the person from the Earth. This is L0 measured by stationary observer relative to the clock. L0. This is how long clock appear from the Earth. Now we put it into this equation. We have the total time that measured from Earth will be L over C minus V plus L over C plus v. Let's bring it to the common denominator. Let's bring it to common denominator and simplify. So that will be equal L times C plus V plus L C minus V over C squared minus V squared. Expanding brackets and simplify, we will get 2L divided by C squared minus V squared. So we found that and 2LC over C squared minus V squared. And let's do a little bit one more rearrangement. Let's put C down. And we get 2L divided by 1 minus V over C V squared minus C squared, and we need to have another C. So this is, I've just put C down. And so this is the time, how long it takes to light get from one mirror to another and back from the person on the Earth who is stationary for the clock. And this is the time that will appear to the person on Earth, how long it takes light on the spaceship go there and back. But you already know the relation between those times. We know the time t times t equal t0 times gamma. We already learned the time dilation. Also, what if we look on this one, we will get 2L on C times 1 over 1 minus V squared on C squared. What is this?
Gamma. Oh.
Gamma squared. It is gamma squared. So we have 2L on C times gamma squared. Let's substitute here T0 and T. We have T equal 2L on C times gamma squared equal 2L0 over C, and we have T equal 12C times gamma squared, and this times by gamma. I substituted T and T0 into that formula for time dilation. Now let's cancel. What can be cancelled? Speed of light cancels, 2 cancels, and 1 gamma cancels. And we get relation between the two lengths. We get that L0 equals L gamma. Or rearranging L equals L0 divided by gamma. Gamma is always greater than 1. So L0 is a proper length because it's measured by the stationary observer, measured stationary object to the measure the length of the object which is stationary relative to observer. And L is how long the same thing measured if the object moving. So what we can see, what's greater, L or L0?
L.
Gamma is greater than 1. L0 always greater. So for person stationary, and you're stationary, and you observe something moving, you will measure the length of the thing is moving shorter. That's why it's called length contraction. That's why it's called length contraction. So you don't need to know any of these.
L0 is greater than 1.
Huh?
Sorry.
But all you need to know that if you're moving relative to something, something moving relative to you, the length appears shorter. the proper length divided by gamma. Again, proper time, to measure proper time, to measure proper length, you need to be stationary relative to what you measure. You need to be stationary relative to the clock to measure proper time. You need to be stationary relative to the thing which length you measure. For example, you are on the spaceship and you measure the spaceship is length 20 meters. You are inside the spaceship and you measure that it is 20 meters. And you're moving with the speed that gamma equal 5, let's say. And your friend observing your spaceship, how long then your friend will measure your ship when it's passing by?
4 meters.
4 meters. Your friend will measure that your spaceship is 4 meters long. For stationary observer will be appear that it's short. Important thing, it's only appear in the direction of the motion. So the dimensions of the object will be distorted. If you have, let's say, you have a cube. Moving this way. How it will appear to stationary observer?
Thinner.
It,
Anyway.
Wouldn't it be like more like a prism?
no, it's moving. It is a cube,
Yeah.
and it's moving.
Thinner?
Now, when you observe it, it will shrink only in this direction. All other directions will not be shrinking. So it will appear to you, this is how it is, but it will appear to you that it looks like this. All other dimensions, only dimension along the motion in this way, it shrinks. Height does not affect it. The width not affected. Only this dimension will be affected. So two other dimensions, only in the direction of the motion it looks short. In all other dimensions it is same size. And the last comment, when you have equations regarding the muons or whatever, some particles moving, and you need to explain something. How that, let's say, equation with the muons. Why there are more muons came as it was expected. Remember the question, classical question about muons we did with the time dilation. And you need to explain. You can explain those equations in two different ways. You can explain using time dilation, or you can explain using length contraction. Never use both. If you try in one explanation, use both length contraction and time dilation, at the same time you will get 0 marks. Because you will stuff it up. Always use one. So if we have, for example, we have some accelerator with the length measured at the sign, it is stationary, L0, let's say 5 kilometers long. And we have muons moving with a speed, or some particles moving with a high speed, and they moving with a speed, let's say 0.99 of c. Let's calculate what will the speed be. What that will be speed. So v equals 0.99 times 3 times 10 in the power of 8. That will be equal to 2.97 times 10 in the we done it correctly, it's times 10 to the power of 8 meters per second. That will be the speed. So, that's the speed of the particle. How long it will take from the scientist who are stationary, how long it will take from the scientist's point of view for the particle to get through this? How we find it? Distance over speed. We have 5 kilometers, 5 times 10 in the power of 3, divided by 2.97 times 10 in the power of 8. That will be equal about 1 point. Can you please help me use calculator?
Wait, is that the
Something,
proper
some
time?
will be something like 1.4.
1.7.
1.7 and 1.7 times 10 negative 5 seconds. Yes?
Is that the proper time?
No, that's a time measured by the scientist. Is the time measured by the scientist is the proper time? No, the scientist is not moving. Measure time for the particle. How now? And let's say that let's calculate gamma. What will be gamma? That will be 1 over square root of 1 minus 0.99 squared. 1 divided by square root of 1 minus 0.99 squared.
7.
7? Okay.
7.1.
7.1. So what will be, now from the point of view of the particle,
Times
first, how long will be accelerator? Particle moving. This is a proper length because it's measured by the observer stationary relative speed. So we need to divide L0
704.
by gamma, so we divide 5 by 7.1. That will be about 7 point. If you divide 5 by 7, sorry, it will be 5 divided. That will be 0.71 kilometers. So that's why we can explain using why more particles decay, or why more particles came than it's expected. Because for particles, this accelerator appear not 5 kilometers. It's just 0.71 kilometers. It's short. That's why more particles make it through. Now let's calculate the proper time. Proper time, the time that we calculated is the dilated time.
You
Yes.
said that that the proper length is 5 kilometers.
Yes. Because it's measured by the scientist who is stationary relative to that accelerator. When you're stationary relative to something that you measure, that's a proper length.
But and where the scientist? Where so the scientist?
Scientist stationary.
Yeah.
Scientists stationary here and observing particles flying through this accelerator. What will be the proper time?
1.2 times 10 to the negative 4.
That will be, we need divide 1.7, the dilated times 10 negative 5, divided by 7.1, that will be, is it divided? 1.7. Will be
2.3 times 10 to the negative
6.
Or 2.4.
2.4. Okay, 2.4. So we have that from the particle point of view, it takes much less time because they will be measured proper time. So you can explain it two ways. Why more particles were able to get through. One thing, either for particle using time dilation, that you can explain that because from the particle point of view, it takes them less time to get through the accelerator. Or you can explain using length contraction. From the particle point of view, the accelerator is contracted and it's much shorter, so more particle able to get through. Yes,
So if the proper time is when the object is moving, how come proper length is when like an object is stationary?
that's what we divided at the beginning. That always remember, it's not necessarily moving or not moving. You need to make proper things measured when you are stationary to what you measure. If you have your clock with you and you measure time, that will be proper time. Are you stationary but you measure for yourself? Or you moving, you measure for yourself, it's a proper time. As soon as you moving and I'm watching your clock, that will be dead length in time. But you look on your clock when you're moving, that's a proper time. With the length, again, if you stationary relative to what you measure, it doesn't matter you're moving or you're stationary. You're staying on the, we are on the earth, I measure how long is this board. That's a proper length. Or even if we will be moving, let's say all our building, moving with a high speed that direction, but still I will be in the same, will be stationary relative to the board and I measure it, that will be proper length. But if you stay outside and observing this board, for you it appears to be short. Yes?
Okay, but still I don't get why you use the proper length to find out the dilated time. You said that the time, remember you calculated time measured by scientists was proper length over time, over
speed.
Yeah.
Proper.
Why is the
length just time equal distance over time?
No, I know that, but why do you use?
You
use proper length to measure
to calculate
time.
To calculate the time.
Yeah, but that's.
But that is not a proper time. Why it's not proper time?
Yeah, that's what I'm asking. Why is it a proper time?
Because it's a time of what? Time that takes particle to move from here to here. And proper time will be measured if particle has a clock and measure it while moving.
But okay, so but what I'm saying.
When scientists measure time for moving particles, so it's not a proper time for particle. Proper time for particle at its own time, measured by the particle. So scientist is stationary, particle is moving. Scientists looking on the particle. So that will not be proper time. If scientists will be moving with a particle, then that will be proper time. Make sense?
The reason why you used proper length to
because
proper length is what they say. That's
what they say, because scientists stationary relative to the accelerator. Yes.
If you use like the proper time for the nuance and then use it like the contracted length, if you like divide them by each other, do you get like their speed? You know what I'm saying? Like if you use
okay, let's divide 0.71. Guys, please divide 0.71 by the 2.4 times 10 negative 6. Divide the contracted length by proper time.
3 times 10 to the 5?
Hmm?
Hang on.
This is 0.71 kilometers, so it's 710 meters.
It's
okay.
It's 295.
So we get this speed.
Yeah.
Excellent observation. We will get the speed of the particle. If we divide the contracted length by the proper time, we will get the speed of the particle. Very good observation. Okay, that's all new things for today. Like, subscribe and donate to help fight terrorist countries and organizations, support Ukraine and Israel.